Hello everyone, in this lecture we'll discuss timers in Atmega 328. Of course, since the beginning of this series we are working with Atmega 328. Specifically we're going to target timer 1 only. What timers are used for in a microcontroller, usually it's for waiting a certain time and then after expiring you want to do something. So for example, you have a task to be done, like toggling a light or turning something on or turning something off. So you have this task, let's say this is your program, okay, and you have a task to be done every 1 millisecond. So traditionally what we do is we use delays. So delays, what happens is that you have somewhere in your code called delay, and then function delay is there to do this to do a delay for 1 millisecond, and then after you call this delay you perform the task that you want to do. So this method works, however your code is stuck waiting for the delay to finish. However, in a microcontroller, timers are separate entities. So it's a physical component inside your microcontroller, and as well as like RAM and let's say ADC, analog digital converter, we have RAM, and we have a component called timer. This component is a hardware component. Here we notice that the delays are used and are written in software. So everything that you do is software based. However, timers are hardware based solutions for creating timed event. So what I mean by timed event, like an event that happens after a certain amount of time. So the first differentiation between delays and timers, that delays is written in software in your program, and timers are hardware components. So the way the advantage is a lot, because when we couple it with the next chapter, which is interrupts, timers can work in the background. So your code will be doing some stuff like copying some values, reading some values while the timer is running. So the timer is running parallel to your code. Okay, so timer are hardware-based solution for creating timed event, whereas these delay routines are software solution for this time event. So how do we configure timers and how do we use them? So timers are configured using special registers. These special registers have the ability to configure your timer to behave in a certain way. So for example, let's say we want to have a, this is the timer, okay? Of course, the timer needs to count from somewhere. It's a 16-bit timer, okay? So of course, we need to load it with a value. So this value is found in since it's 16-bit, of course, I cannot place it in just a single register. So these two registers that hold the value of the time or the amount of time I want to reach is in two special registers called timer counter 1 high, timer counter 1 low. So these two registers hold the time that needs to be counted. And the way it works, so let's say I can work it with 16 bits or 8 bits. So let's say I'm gonna work it with 16 bits. So effectively I load it with a certain value. So let's say I load with 0x0000. Okay, so when I start the timer, I start adding value at each clock cycle. So typically, since it's a hardware component, we have a clock that's being fed into the timer. So each clock cycle, let's say this is clock cycle 1, what happens is that this becomes 0x00, 0x01. Clock cycle number 2, 0x00, 0x02, until I reach 0xFFFF. Then when I overflow, timer will be expired. So I have a timer, I initialize it with certain value, in this case it was 0x00. At each clock cycle I start counting values 1, 2, 3, 4 until I reach the maximum value, which is all F's, FFFF, and then when it overflows, the timer will expire and I have a flag or an indicator telling me timer is finished. So this is the basic operation. We have a clock, we have starting value, it can be any number. Okay, we have a flag telling me that it's finished. This is called TOV1, timer overflow 1. So once I finish counting, timer overflow equal 1, it will be set, and I know for sure that the amount of time that I wish to spend has expired. So this is the basic idea about timers. So how can I configure it even more? So there are different ways to configure this timer and different registers. So the first register that I indicated is timer counter 1 high, timer counter 1 low, which holds the initial value where I start counting. Register that is important for the configuration of the timer is called TIFR, which is timer interrupt flag register. It has several bits, but I'm only interested in bit number 0, which holds TOV1. As we know, TOV1 is the indicator that timer 1 in this case, because we are only working with timer 1. Timer 1 has expired. So we start with 0 and then goes to 1. When it reaches 1, this means when it turns to 1, this means timer 1 has finished, and the time that I set it up has been taken. And the third register that I want to discuss is the timer counter control register. It's called TCCR1A, and we have also TCCR1B. Those two registers are also used to configure timer 1, what mode we want to use it, and we're going to discuss two modes, the normal mode and the counter mode. So with TCCR1A, we are interested in 2 bits, bit 0 and 1. It contains a bit called WGM11 and WGM10. I'm gonna just, they are all 8, both are 8 bits. Don't get fooled with because I want to use more bits. So with this, I'm interested in bit 0, which is called CS10, and then CS11, 1, CS12, and then WGM 12, WGM 13, and these are the bits that I'm interested in. So we 0, 1, 2, 3, 4. So what does these bits mean? So here, for the type of operations that we're going to use, we're going to use a combination of these 4 bits, WGM 1 and 1011. So we're gonna these bits and this bits, we have 4 bits. So setting WGM from 13 to WGM 10, so these 4 bits that I circled in red, if we set them as 0000, then we are in the timer 1 normal mode. Of course, there are many modes that I can discuss. I will not go through in this lecture. This can be PWM or CTC, capture compare. So PWM with 8 bits, 9 bits. So we have many ways to configure timer 1. But in our case, we're just going to use the normal mode. Alright, so so always we're going to set WGM 11 and WGM 13 and 1220. So we can conclude here that TCCR1A, we're going to always set it to 0. Okay. Now, what about CS10 to 12? So we're going to discuss now CS12 to CS10. They are 3 bits. Okay. So if I have them as 000, this means we have no clock and we stop the timer. Timer stopped. So if we set those 3 bits to 3 zeros, then we can stop the timer. Then if we set it to 001, then we go ahead and feed it a clock and we start the timer. Now we have also 010. Now we're gonna feed it with clock over 8. This is a prescaler. I'm gonna discuss it later in the lecture. 011. We have clock over 64. 100. This is clock over 256. 101. Clock over 1024. If I feed it 110, it will act as a counter on a specific pin, which is T1 pin, which is PD5, port D pin 5, port D pin 5. However, it's on a falling edge. And 111 counter, also T1 pin, which is PD5, rising edge. So the continuation of this lecture will be as follows. I'm going to start with the first one, which is the normal mode. Then I'm going to go ahead and talk about prescaling. When do you use it? Why do we use it? And then about the counter application of timer 1. So timer 1 can act as a normal timer or as a counter that counts pulses, and we're gonna see this in a bit. Now I'm gonna summarize the steps needed to configure timer 1 to render it operational. So first, to program timer 1, and remember this is just for timer 1. Usually we have multiple timers inside the microcontroller, and at Mega 328 we have 3 timers, 0, 1, 2. We're only considering just timer 1. So first step, we load timer counter 1 high and timer counter 1 low with the initial values. I'm going to discuss this next. 2, we need to load TCCR1A with zeros and load TCCR1B with the desired value. So we can start with 0 to stop it, or 1 to begin with it. So if you want to start it, we've set it to 1, which is, in this case, we are using clock mode, and this means start timer. Now, step 3, we monitor TOV1 flag that's located in TIFR. The way we monitor it is as follows. We do SBIS. Of course, the register responsible for TIFR1, TOV1, and then I do rjump again, and this is again. So I keep monitoring the flag. Once this is 1, it will skip, and here I have timer expired. So this technique is called polling. Of course, we are stuck in the program here, and we're not gaining anything from using timer 1 since we're using the polling technique. But when we use it with the interrupt, when we couple it with the interrupt, you will notice the advantage of using timer 1. So the fourth step, after expiry, we stop timer 1. The way we do it is by setting TCCR1B to 0, 5, reset TOV1. And it's very interesting to see how we reset TOV1. So effectively, when we want to reset it, we do the following. Say LDI R20, comma 1, okay, and then we say out TIFR 1, comma R20. So effectively, when we want to reset it, we place 1 in it. Okay, you can think of this as a push button, that you push it and it does not hang. If you push it, it turns on. You push it, you turn it off again. So whenever you give it a 1, it toggles the value. So if it's 0, and automatically it turns 1, remember. So when we start the timer, TOV1 is set by hardware. So remember that this is set by hardware. Once timer expires. To bring it back to 0, we place 1 in it to reset TOV1. And remember, TOV is in the first bit. So let's start now each step of the way and build the program. So we're going to start with the step number 1, and how do we actually know what values to load inside timer counter 1 high and low. So let's talk about initial values of timer counter 1 high and timer counter 1 low. So remember that the timer works on a clock, and this clock is fed by F oscillator of the microcontroller. So remember that we have the microcontroller and we have the crystal that is feeding it. Remember chapter 8, this is what, remember the previous chapter where we connected an oscillator. So this oscillator has a value. So imagine that the value is 1 megahertz. Okay, this means the period, let's do 2 megahertz. So 2 megahertz. So 1 over F, which is 1 over 2 megahertz, which means equals 0.5 microseconds. So this means that each time I go from here to here, I spend 0.5 microseconds. So remember, every time I count a specific value, it's done with 0.5 microseconds. When I start the timer, let's say we initialize it to x0000, and it overflows to 0xFFF, then we add 1 and it overflows. So these are, the value here is 65535 plus 1, so 65536. Here it overflows. So given, and remember, at each cycle we do an addition, we do an incrementation. So this means if we multiply this by T oscillator, which is this one, okay, this means I have 65536 times 0.5 microseconds. This means if I calculate it, the value will be 32768 microseconds, or 32.768 milliseconds. So the maximum value that I can time inside a timer 1 by initializing it to 0xFFF is 32.768 milliseconds. So if I want to write a formula for this, so delay that is imposed by the delay imposed by timer 1 is equal to 65536 minus timer counter 1 high and timer counter 1 low times T oscillator. In case of that, this is the value. So in case of timer counter 1 high and low is equal to 0, this will be 65536 minus 0 times, in our case the oscillator was 0.5 microseconds. We get 32.768 milliseconds, as I demonstrated before. So the problem becomes, what is the value of timer counter to have, for example, a 10 millisecond delay? Okay, so let's say I want not 32.768 milliseconds, I want 10 millisecond delay. So of course we notice that T oscillator is in microseconds and this is in milliseconds. So I have two choices: either change this to milliseconds or change this to microseconds. 0.5 microseconds will be 0.1235 milliseconds. So now I have both the same units. So 65536 minus n times 0.0005 milliseconds is equal 10 milliseconds. So notice here that we have the same units. If we left it at 0.5 microseconds, which is a common mistake, we will have different values and the values will be error, will be wrong. So if I divide 10 milliseconds by 0.005, I will get 20,000. So 65536 minus n is equal to 20,000. This means n is equal to 65536 minus 20,000, and this will be 45536 in decimal. Now I need to load these values in timer counter high and timer counter low. So what I need to do is, actually I need to transform them into hexadecimal. Transforming them to hexadecimal will be 0x B1 E0. So this will be timer counter 1 low, and this will be timer counter 1 high. So the steps are as follows. So we're starting with so we start with how much time I need to have a 10 millisecond delay. So first of all, I need to match the signs. So if there is a microsecond here, I need to have change this to microsecond, or I need to change the period to millisecond to match the time delay that I'm asked to do. And then we know that it overflows at 65536. Then I subtract from this value, and then we have the amount of time needed, which is 45,000 clock cycles to start with. So what does this mean? So this means we start with 0x B1E0 when we start the timer, and as you know, we start the timer by setting TCR1B with 0x01. So it starts counting. So it starts from here. This is 0, then 1, 0xB1E1, 2, 0xB1E2, and continue until it reaches 0xFFFF. Then another one, it overflows here. So this is the clock. So I start here with 0xB1E0. So the first edge, it will be 0xB1E1. The second, 0xB1E2, until I reach 0xBFFF plus 1. Okay. And the number of cycles that I reach here is actually the difference between 65536, which is 20,000 clock cycles. So I need 20,000 clock cycles to actually have a 10 millisecond delay. So here we have 20,000 clock cycles. Okay, so if you get this 20,000 clock cycles and we multiply them by the time period, which is 0x 5 microseconds, we get a 10 millisecond delay. So this is how we set up the timer for a specific delay. We can change the time oscillator. If it's let's say 16 megahertz or 8 megahertz, then this value changes, and I can give you, okay, I need 2 milliseconds, 3 milliseconds. Remember that this value, okay, n should always be less than 65536. So n should always be less than 65536. Otherwise, we need to slow down the clock, and we use a Prescaler. So an important note is n always less than 65536, which is the maximum amount that can be that can hold inside the 16-bit. Now, so this is how we initialize the timer. I can give the problem in a different way. So let's give another problem. Assume now you have an 8 kilohertz oscillator and timer counter 1 high, timer counter 1 low is initialized to 0x, let's say A0FB. Okay. What is the timer 1 value that it waits, or the delay? So first, I go ahead and okay, I have f oscillator is equal 8 kilohertz. This means timer of the period of one oscillator is 1 over 8 kilohertz, which is equal to 0.125 milliseconds. Okay, since it's kilohertz, it goes to milliseconds. Megahertz goes to micro. And then I will say, okay, I have 65536. It's very useful now to change this to decimal, and 0xA0FB in decimal will be 41211, and then we multiply it by the period. This value will be, if I do it like this, value will be 24,325 times 0.125 millisecond, and the final value of the weight will be 0.625 milliseconds, or we can say this is equal to 3.04 microseconds if we round it up. So this is the two ways we can find the value of the time delay. We can start with the time delay, as I said here, like we want a 10 millisecond delay, and how much is timer counter 1 high and low. Or we can say, okay, I have this value, what is the amount of time needed to with this value to have. So let's now turn to an example where we have a 60 megahertz crystal or F oscillator. So F oscillator is equal to 60 megahertz, and we want to write a program that toggles PB5, which is port B pin 5, every 1 millisecond. So we first want to know what's the initial value. So let's go ahead and find T oscillator, which is 1 over 16 megahertz. This will be equal to 0.0625 microseconds, as we have megahertz, or we can say this is equal to 0.000625 milliseconds. Okay, now we need to find the values. So now, since it's just 1 millisecond, say 65536 minus n times T oscillator is equal to 1. So dividing 1 by T oscillator, okay, will be 16,000. This is equal to 1 over 0.000625. Okay, implies n is equal 65536 minus 16,000, and this will be equal to 0x will be 49536, which amounts to in hexadecimal to 0x C180. So remember, this goes to timer counter 1 low, and this goes to timer counter 1 high. Now let's write the program. So remember, we need to toggle PB5 every 1 millisecond. So first, since we're going to use functions, we're going to initialize the stack pointer. So LDI R16 high RAM end out SPH R16 LDI R16 low RAM end and out SPL R16. So now we initialized stack. This is just for the use of functions. Second, we have port B. We need to set the outputs and the inputs. We don't have inputs here, so we want to set DDR B, 5 as output. So here I'm saying pin PB5 is output. Now the next step is I need to start with a value for here's the beginning of the program. These are the initialization. So I'm gonna say, okay, SBI port B, 5, start with PB. It can be 0, it can be 1, doesn't matter. Equal 1. Then I'm gonna say, okay, rcall delay timer 1, and then I will say CBI port B, 5, and rcall delay T1, and then we repeat again. So here what I'm saying is that I start with, this is PB5, it will be 1, I wait for 1 millisecond, then I toggle it, then 1 millisecond, toggle 1 millisecond, and so this value is actually delay dash T1, and this is delay dash T1, and it is 1 millisecond because I will configure it to be 1 millisecond. So to configure it to 1 milliseconds, I need to write the function for delay T1. So let's write what's in delay T1. Okay, so first, to configure delay T1, it will be, I'm gonna first initialize the values I have. The values I have is 0xC1 and 80. So LDI R16 0xC1, and then I'm gonna use STS in this case. Remember, we're not gonna use out with the registers that are used with timer 1. So the timer counter 1 high, R16, then LDI R16, what was the value? It was 80, 0x80, STS timer counter 1 low, R16. So the value that we had, we initialized timer counter 1 high and timer counter 1 low. Now we need to start with TCCR1A, so we're going to set it to 0, so I'm going to say LDI R20, 0, STS TCCR1A, this means timer 1 normal mode, and then I'm going to say, I'm going to start the timer with no prescaling, so in this case I'm going to say LDI R20, I can use any register, 0x01, and STS TCCR1B, R20, start timer 1, no prescaler, we're going to discuss next as prescaler values, and in this case, here from this point I start timer 1, so I need now to monitor the flag of TIFR1, TOV1. So I'm gonna wait here for 10 milliseconds. So 1 millisecond, excuse me. So this will keep on here for 1 milliseconds. Once it is set, I need to clear. I need to stop the timer first, because if I don't stop it, it will keep on going on and on again. So LDI R20, 0, and STS TCCR1A, R20. Here we stop the timer, and then we need to clear the flag. Say LDI R20, 1 as begins out TIFR1, R20, and return. Okay, here reset flag. Alright, so if you want to break down our program, we have first, so here load initial values that we have computed, then configure as normal mode, configure and start the timer with no prescaling. Here in these two steps we monitor TOV1. Once it's 1, it will skip it. I stop the timer and then reset flag here. So this should have 1 millisecond delay, excluding the overhead. What's the overhead here? It's this instruction. We're not taking care of them. We're not considering them. And if you in applications where it's accurate to have an exact 1 millisecond delay, we need to count those instructions and see how many cycles they take, multiply them by the period of the F oscillator, and subtract them when you're doing this formula. But we're not going to go over this problem of having an exact value of 1 millisecond. So as you notice, the program for using timer 1 is very easy. So for solving the problem, I can use delay 1, delay dash T1. I could have done it in the loop method, but in this technique we are using timer 1. So the main problem is not changed in terms of coding. However, the function delay timer 1 is of course more complicated and it's more beneficial, as we see in the next chapter. What happens when we want a delay that does not fit the 65536 limit? So we mentioned there is something called a prescaler, and the way it's used is as follows. So F oscillator actually pass through a prescaler, I can say PSA, before entering the timer. So this 1 over X, where X can be 64 or 8, can be 8, or 64 or 256 or 1024. So let's say I have a 16 megahertz clock. Okay, so 60 megahertz, if we have no prescaling, so the time is 16 megahertz over 1. So this is prescaled. So here the first, we're dividing it by 1, so we don't have any prescaler. The period will be 1 over 16 megahertz, which is equal to 0.0625 microseconds. Okay, and the timer value will be, if I want to do a, let's say a 1 second delay, it's 1 second over 0.006, sorry, 0.0625 microseconds is going to be 60 million, which is greater than 65,000. If I want to use a 8 prescaler, so this is 1 prescaler, if I use the 8, now in this case I will have 60 megahertz over 8, which is now, I slowed the clock, so here it's just slows the clock, and now I have 1 over 2 megahertz, which is equal to 0.5 microseconds, and here 1 second or 0.5 microseconds is equal to 250,000, still greater than 65536. So now I try the 64, so 16 megahertz over 64 is equal to 4 microseconds, it's equal to 250 kilohertz. So 1 over 250 kilohertz to find the period, it will be 4 microseconds. In this case, 1 second over 4 microseconds, it will be 62,000. Sorry, this is, I made a mistake here. This is 2 million, and this is 250. Okay, still greater than 65k. For 256, I have 60 megahertz, and divided it by 256 times, which is 62.5 kilohertz. 1 over 62.5 is equal to this is microseconds, equal 16 microseconds. So 1 second over 16 microsecond will be 62,500. So this works. And if I use the 1024, 16 megahertz over 1024, it's equal to 15625 hertz. Period will be equal to 64 microseconds, and the value here will be 15,625. So we notice that this Prescaler, choosing 256 and 1024 to do a 1 second delay is good. So let's see how the problem changes. Let's say I want to toggle PB5 using 16 megahertz clock and for 1 second. So as we said before, we're gonna use a Prescaler of 256. So in this case, we will do the following. So we don't have to change all the program that we written here. We just have to change these values, and of course I need to change this value now. So what are the values that needs to be changed? So let's count them all. So we said that 65536 minus n times t oscillator is equal 1 second. So if we used 256, in this case t oscillator is equal 0.0625 microseconds. Now, and of course f oscillator is equal 16 megahertz. So if you use a Prescaler of 256, so f oscillator is equal 16 megahertz over 256, or we can say t oscillator is equal 0.0625 times 256. So multiplying those two together, we'll have this microsecond. This is 16 microseconds. And now what we have is 65536 minus n times 16 microseconds is equal to 1 second, implies n or 65536 minus n is equal to 1 second over 16 microseconds, and we already calculated this. This will be 62500. So n is equal to 65536 minus 62500, and this will be the following. It will be equal to 3036. In hexa will be 0x0b dc. So now rewriting I'm not gonna rewrite it again, I'm just gonna change the values into the new one. So as we said, instead of writing 0xc1, now we have 0x0b, and this will be 0x dc. And instead of now writing 1, we need to find the value that uses a prescaler of 256. And in this case, I'm going to go back to my initial I'm going to go back to where I explained CS 1011 and 12, and I said, okay, in these values I can use the following timer. So if I want to use a prescaler, as I said here, I'm dividing the clock by 8, I'm making it more slow, so I need this. So to do this, I go ahead and change this to 4. So instead of using 1, I use 0x04. So the same program is repeated, but this time I loaded with BDC and 0x04, and in this case I'm using the timer 1 using the prescaler mode. Now the last topic I'm going to go through is counter mode for timer 1. So in this case, timer 1 in the timer mode, it just we load it with a value, and once it overflows, the time expired that I want. However, with counter mode, it counts pulses from an external pin, which is PD5. So in this case, timer is fed from PD5 some sort of a pulsed signal where it counts either the rising edge or the falling edge. So each time a pulse passes, it could be generated from a push button or it can be from a switch. Each time there is a pulse, whether the rising edge or the falling edge, depending on how we configure it, the timer adds another pulse. It has many applications. Let's say counting. Let's say if every time we press a push button, you increment a counter. It can be used for counting pulses. It can be used also for we're using sensors. If I have a RFID sensor, or sorry, an IR sensor, infrared sensor, every time you cut the light, you increment the value of timer 1. So to go through it, assume you have a clock pulse fed into a PD5, which is T1. Write a program that counts the pulses and displays them on port C and B. Okay, so first what we need to do is, of course, we need to set up the ports. Both ports are output and we have PD5 as input. So first we start CBI port DCOM5, then we say LDI R20 0x00 out TD, it's going to be output DDR B R20 LDI R20 FF, we can omit this, out DDRC R20. So now we configure the outputs, the ports as outputs. Now we will start configuring the timer as a counter. So first we need to set timer control register TCCR1 to 0. So say R16 AR16. This is normal mode. Then we need to set the timer as a counter. So if we take a look, 6 will be falling edge, 7 will be rising edge. So let's say I didn't specify here pulses, let's say falling edge. So here I say, okay, RDX 0x06 STS TCCR1B R16. So here timer 1 as a counter. Then I'm gonna do again. So here we when we load this, timer as a counter and start counting. So now each time a pulse comes, I need to read the value from the stored pulses, which will be in timer counter low and timer counter high. So I'm gonna load into R17 timer counter 1 low and place them on port, let's say B, and I'm gonna read from timer counter 1 high, place them also on port C R17 also. So here I'm placing the low byte and the high byte, and then I will go ahead and say SBIS TIFR 1 when it reach 65535 or 36 TOV1, and then R jump again. So it will continue on doing this until it's cleared. Once it's cleared, it will skip this. So once it overflows, I'm gonna continue here. I'm gonna say LDI R16 0x01, and then out timer TIFR 1, R16, and then R jump again. By the way, we can instead of using this, we can say 1 TOV1, same thing, because this is 1, so it's 1 shifted 1 is 1. Okay, so what's happening here is that, alright, I reset TCCR1 to 0, configured it as counter. At each turn I'm loading R17 with the timer counter 1 low and timer counter high 1 high. You may say, what if no pulse came into the pin? They will stay the same. Once I reach 65535 and 65536, this will overflow. I need to reset it before starting it again. So you notice here I keep on doing it unless TOV1 is 1. Once it's 1, I reset the flag and continue on doing the same thing again. This finalizes our lecture for timer 1.